Welcome to a brief understanding of general relativity. General relativity is an extremely complex theory that has so many parts to a puzzle that it would be impossible to give an in-depth lesson in just a 4-minute video, but I will do my best to cover as much as I can. Let's begin with how general relativity began. In 1905, world-renowned physicist and mathematician Albert Einstein had published his theory called special relativity. This explained how an object could not approach the speed of light, but it can come close to it. It is also the origin of the equation E equals mc squared. However, this theory did not account for the effects of gravity and were in circumstances where acceleration was zero and the velocity was constant. And there was a certain phenomena that didn't explain Newtonian's gravity. So in 1915, Einstein came up with the theory general relativity. A major part of general relativity is the equivalence principle. The equivalence principle states that in small frames, free falling in gravitational field is the same as moving uniformly in space, or being stationary in a gravitational field is the same as accelerating in space. This is only true in a small frame because of tidal effect, which we will go into later. The equivalence principle helps to explain many things in general relativity, one being gravitational redshift. Gravitational redshift is when light is emitted from a lower level in a gravitational field as it travels to a higher level, and the frequency of this light wave will appear reduced when it reaches to the higher level gravitational field when moving farther away from you. This means the wavelengths of the light are stretching out and getting elongated. These longer wavelengths correspond to the color red, indicating it's moving farther away from us, hence the name gravitational redshift. An example that may help you understand is if someone was shining a light from Earth that was green, a low-level gravitational field, and the observer was next to a black hole, an extremely high-level gravitational field. The light would appear more red because the wavelengths have stretched out, according to the observer in the black hole. There is also a gravitational blueshift, which is the opposite when light is emitted from a higher gravitational field down to a lower gravitational field and moving closer to you, and it appears more blue. In general, wavelengths change in frequency through differences in gravitational fields, and this is called the Doppler effect. The Doppler effect doesn't just apply to the color spectrum of wavelengths, however. Due to the change in frequency of wavelengths between higher and lower gravitational fields, time also changes. To explain this, let's look at the famous case, the twin paradox. Twins are wearing the same watch, and one twin travels to space at a speed close to the speed of light, while the other twin stays on Earth. When the other twin comes back from Earth to Earth, they compare the time on their watches, and it appears the girl's watch is behind in time compared to her twin's watch, meaning she is now younger than him. When accelerating close to the speed of light, time is slower due to the reduction in frequency of the waves. The frequency of the waves is equivalent to time. Thus, the girl is now younger because her clock slowed down when she was accelerating, and the boy's clock never changed. All of this can be traced back to Einstein's equation E equals mc squared. This equation shows how gravity can extract energy from escaping matter and light, and cause gravitational redshift, where gravity is extracting mass. From what we have learned from the equivalence principle is that spacetime is not something constant or linear. Spacetime is curved. We can see this with time dilation and how its time is relative. Things like time and light travel through the shortest path in spacetime. Matter and energy warp spacetime, and spacetime directs the motion of the matter and energy. The equivalence point is only applied in small frames because tidal forces affect how light and matter move through time. Tidal forces are the differences in gravity in space, which is also a part of space-time curvature. And we can see this with the moon and our waves on Earth. The main points we have touched on general relativity were the equivalence point, gravitational redshift, time dilation, mass and energy, and connecting it back to space-time curvature. I hope this video has given you more insight on general relativity, and of course, you can get even more depth with each subtopic in this, and I encourage you to do so. Thank you!